Okay, thank you for coming. All right, so we're here for a tutorial, and let's do this. What did I say, 40 minutes, 45 minutes, 40? So you get to go first, and you get to go second. The floor is yours. Just so the public out there will know, the ground rule for this tutorial is everything has got to be in the public domain. So there's no trade secrets going to be shown today. If that's what you came for, too bad. You won't see anything. But this is to educate the judge on things in the public domain. So there we go. All right. Go ahead.
Thank you, Your Honor. Once again, my name is Jordan Jaffe, and I'm going to be presenting this today with my colleague, Mr. Cordor. Got my clicker. So before I get started, I wanted to kind of give you a roadmap of where we're going to go today, the topics that we're going to touch, at least with regard to our portion of the tutorial. So the first thing that I'm going to talk about are basic principles of LiDAR. What is LiDAR? How does it work? The basic kind of underlying principles of play. Then we're going to transition into early applications of LiDAR, what it's been used for historically. It's actually, in its most primitive forms, it's actually not that new. It's been around for about 50 or so years. Then we're going to fast forward in time, how it's developed over the past few years, and then we're going to transition to how it's been used in self-driving cars, most relevant to this case. And then continuing on the timeline, we're going to talk about the early self-driving cars, how they use LiDAR, how they use some other sensors that are relevant here. And then lastly, we put together some slides on the two patents that we highlighted in our preliminary injunction motion, speaking about the example and the specification, and we can go through those in as much detail as Your Honor wants at the end.
And while you're pausing, I have a question about the way it's spelled. And I want to make sure there's no trick involved here. How do you spell the generic version of LiDAR?
Sure. So we actually have a slide on this exact point, which is
all right.
LiDAR
and
or
you
LiDAR.
Anticipated me. All right, go ahead. Okay. Is that it?
The short answer is there are two words that essentially describe the same thing. LiDAR would be light detection and ranging. LiDAR would be laser detection and ranging. But laser is a form of light, so we're talking about two forms of the same thing.
Right, but I've noticed that sometimes it's spelled with a small I, and sometimes with everything else capitalized, and sometimes it's just the L is capitalized. And I want to make sure that if I use LiDAR in one way or the other, that one side is not going to come back and say, "Oh, Judge, we thought you were talking about the trademark thing. We didn't know you really meant generic." I don't want to be the victim of that. So I want us to all agree. Right here, Mr. Gonzalez, you need to stand up and let's all agree that you tell me, does L small I DAR mean any and all versions of LiDAR, or does it mean just the Waymo trademark version?
The answer is yes, any and all.
Any and all. All right, so if I were to give you an interrogatory, which I'm inclined to do, you got to go dig up some information within your company on LiDAR. You're not going to come back to me later and say, "Oh, we thought you just meant the Waymo version."
Correct.
Okay, all right. That's what you understand it that way too?
Yes, Your Honor.
All right, so that's good. So my law clerks we're going to use L, small I, capital D, capital A, capital R. That way. Now I'm reserving the right to use any other version too, but if I happen to I just don't want to be accused of referring to something much more narrower than I intended. All right, go ahead.
So to jump back into this slide, I'm going to start by just talking about the basic underlying principles of LiDAR. And we have a little animation here to help with this, and this is kind of a different kind of detection, sonar.
Echolocation.
So we have our little bat here, which is going to send out sonar, so noise, and you're going to see that it's going to bounce off the small little object on the right-hand side, and the time it takes for those waves to go out and come back is how the bat kind of quote knows how far away the object is. And so it's the calculation of the time that it takes to bounce that we're looking at. So how does this go to LiDAR? So LiDAR is another form of this kind of analysis, but instead of sound waves, we're going to use light. And what we put here on this slide is kind of a definition of what we're talking about in terms of LiDAR or LiDAR with whatever capitalization we may want to use. But the point being is that it's a device consisting of a photon source, that is a light source, as it notes here, frequently but not necessarily a laser, and a photon detection system, that is something that detects light coming back, and a timing circuit. And then we also have some optics to help make this all work. So what are we talking about? How does this work in the LiDAR context specifically? So what we've got here is we've got another little animation, and we're showing that there's a laser on the left-hand side. It shoots out, it hits the object, and comes back. And we're timing how long that takes. So let me just do the animation again here. We can see it takes 100 nanoseconds. And what we do in the little timing circuit on the left-hand side is we're going to ask, okay, I know the time of flight, which is this 100 nanoseconds. I know how long the speed of light is. I can use this formula on the top in order to figure out how far away the object is. So what we've done now is plugged in these numbers, speed of light on the left-hand side, the time of flight that we just accessed, divide by 2, and we now understand that the object is 15 meters away. And then we've added this little annotation that says, a rule of thumb, to put it in a different form, is approximately half a foot per nanosecond. Now, one thing that's going to come up a little bit later that I just want to touch on now is the idea that in our prior slide here, you can see that the laser just goes out and shoots right back. In reality, what we have is we have one laser that comes out, and then it doesn't bounce back like in a science fiction movie. What happens instead is it bounces in all sorts of different directions. And what we've labeled it here is this kind of diffuse reflection. And what this means is we need to shoot a lot of lasers out in order to get photons back coming in the second direction. And some of the literature actually talks about when you shoot out 1 million photons, only one will come back in the same direction. So we need to use a lot of photons in order to kind of make this work. Now, taking this a step further, I've depicted here an example of a LiDAR. And I'm going to just walk through each of the pieces. Basically, what we're doing here is we're going another step under the covers and saying, okay, we understand the principles involved. How does it work? So the first thing we're going to talk about is what's called this control and acquisition part. And what we've done here is shown a circuit. This is similar to the timing circuit that we talked about before. This is telling the signal when to go, measuring the time of flight, things like that. So the first thing it's going to do is tell the signal generator, all right, time to generate a signal. And specifically what it's going to do is do a pulse of light. It's going to generate kind of a wave of light in a laser or other light source. Example here I'm going to use is a laser. It's then going to go out through the transmit lens, which we'll talk about in a little bit more detail shortly. But it's going to go out through the transmit lens, which is going to do a couple things. But then it's going to go to a target, assuming there is a target or other object, and it's going to come back. And then it's going to hit this receiver or detector that we've talked about here. And what this is a photo detector. So what this means is it's a piece of semiconductor material that takes photons in and converts those in an equivalent amount or some relationship to an amount of current. So then it can send a signal back to the control and acquisition part and say, okay, I've got some hits. And then it can do that time of flight calculation we talked about before in order to figure out how far away the target is. So I touched a little bit earlier on the two lenses here, just to give a little bit more detail on what they are doing in the example that I talked about before. The top one is going to do two things. It's going to collimate the light, which is project. And the two things it's going to do are project the outgoing beams and make them parallel to one another. So you can see it changes which direction they're going and makes them parallel. On the other side, the receive lens, what it's going to do is it's going to focus the incoming beams on the detector that we talked about earlier. So it's got to aim them in exactly the right spot where the detector is, or that small number of photons we're going to miss it, and then we're not going to get any range information. Taking a step forward, what we have here is an example of a laser, and what this diagram shows is essentially a laser diode. Now, a laser diode is an example of a laser that's useful for one reason, because it's small, and it's also relatively inexpensive. But some systems get more expensive when they use laser diodes because there's what's called a high divergence. And that's what we've marked in red here on the right-hand side, which means that the light kind of sprays out in a cone formation, and it's an unequal cone. It's kind of an elliptical, as it's noted here. So that creates all other sorts of problems that have to be compensated for in the system. So the example LiDAR I was talking about before is what's called a bistatic LiDAR. Now, I'm going to show a second example here. This one's called monostatic. What that means is that there's one lens instead of two, and there's what's called a transmit and receive combiner. And TX and RX in this context means transmit and receive. Now, this design typically talks about a single beam design. And the reason for that is because we have this combiner that includes some kind of specifics in order to make this work, in order to be able to transmit and receive using the same area. And just to give a little bit more detail on an example of how this works, again, in the single beam context, what we have here is a different diagram showing how a single beam monostatic LiDAR works. Again, we're talking about single lens, single beam. So here, what we're showing is on the left-hand side, we have our laser. It goes through what's called a polarizing beam splitter, and then it goes through a couple other things, but in essence, it goes out into the world through the lens. On the reverse side, in terms of reception, it comes back and hits this polarizing beam splitter, and it reflects down to the bottom. Now, just to give a little bit more detail on what is a polarizing beam splitter, how does this work? So in essence, what it is it's a filter that lets light go through one direction. That's the laser on the left. But when light comes back the other direction, it's going to block it and hit it to a mirror that goes on the bottom. Now, it gets difficult here because there's certain optical problems, which we've eliminated from this picture, but there's certain optical problems and degrees of tolerance that become harder in this design versus the bistatic design that we were talking about earlier. So next, we're going to talk about early applications of LiDAR. I'm going to hand it off to my colleague, Mr. Corridor.
All right, thank you.
Thank you, Mr. Jaffe. Hi, I'm Felipe Corridor. I'll be continuing our presentation today. So now that we've covered what the basic principles of LiDAR are, I'd like to discuss what has LiDAR actually been used for. Some of the earliest applications, as you can probably figure out, is just finding the distance to a target. This is called range finding. This was a very widespread application soon after the invention of the laser in the 1960s and 1970s, especially by militaries around the world. Here I'm depicting an example to illustrate that the same time of flight principle that we've been discussing with Mr. Jaffe can apply to longer distances. So for example, in a military application, it might take 10 microseconds for the beam to reach the target, and then using the formula that we saw earlier, you can compute that translates to 1.5 kilometers distance. Now in the literature, this is sometimes known as single point or zero-dimensional LiDAR because all you're getting, the only information you're getting is the distance to a specific point in the environment, your target. So that's why it's known as zero-D LiDAR. What you can do with such a single beam LiDAR is you can actually sweep it across a plane, as will be shown in this slide. And by sweeping the single beam LiDAR across a plane, you can get information about the points lying on that two-dimensional plane. For example, NASA and the U.S. Geological Survey did this in the early 2000s to map out the topography of areas of interest, as depicted here. And what it looks like is there's a neat animation here. It's still the single beam, and you're finding the distance to each point, and as the plane moves forward, this two-dimensional plane where the LiDAR is scanning moves forward and gets you a little bit of a sense of a three-dimensional map of the underlying environment. Now, how does this actually work? This next slide explains how people used to do this in those early days. Basically, you have some kind of mechanical moving part, usually a rotating mirror. And your laser and detector electronics, the components Mr. Jaffe talked about earlier, stay largely stationary. And then as the rotating mirror moves, you're able to scan across the plane, depicted here by the blue semicircle. And you get information about all the points lying on that plane. Now, what does that information look like? That information is called a point cloud. So what you're getting is range information, how far each point that the laser hits is from your LiDAR unit. And as you scan it across a plane, you can figure out how far each point is. So for example, if you have a room here with a blue curved wall and a little green box in the middle, as you sweep the single beam LiDAR system across the plane of the room, you get the following, which is a bunch of points, blue points representing the blue wall, and then where the wall is obstructed by the green object, you see closer points. This is a very important concept for LiDARs, the point cloud, because this is basically what enables a LiDAR to see the environment by making lots of different range calculations to many different points in the environment. So that's how we get to self-driving cars. I mean, LiDAR systems using the point cloud concept are able to see the environment around there, and that enables self-driving cars to not only see the world, but also feed this information, the 3D point cloud, into the computer and run the software and make decisions, get the computer to make decisions for how to drive the car, when to slow down, when to stop, etc. So here's a depiction of an early 3D point cloud from the early 2000s, from the report we submitted to Your Honor, I believe last week. So as you can see, it's a very detailed point cloud. You can make out two very clear cars on a flat road, perhaps a parking lot, under a tree. Now, the main problem with the LiDARs, if you're scanning a three-dimensional environment with a single beam scanning LiDAR, is you need to scan in two directions. So not only are you moving across a plane, but you also have to scan the plane up and down. And this takes a long time. In this paper, they noted that to generate this high quality of a point cloud, you needed to spend several minutes sweeping the LiDAR across the environment. But when you do get the 3D point cloud, this 3D point cloud has a lot of information. So as you may have figured out, each point has at least 4 parameters. 3 of them are the obvious XYZ parameters, which tell you where exactly in the world is this point in relation to your LiDAR unit. And then many LiDAR systems, we have not discussed this yet, but many LiDAR systems also allow you to make a measure of reflectivity. As Mr. Jaffe mentioned, when you shoot out lasers, very few photons actually come back. But different surfaces and different colors can have different reflectivity. So for example, if you're looking at the road surface, there might be white lane markings on a dark pavement. And the white lane markings send more photons back, reflect more photons back. And so that you will be able to see this using the LiDAR system, because the detector can measure that there was more photons that actually came back, as opposed to a dark pavement next to it, which had very few photons coming back. And another neat thing you can do with point clouds is you can actually rotate them and manipulate them. So these 4 parameters are very easy for a computer to manipulate, and it's a very powerful, it's basically an image of the entire world around the car. Now, how would you do this with the single beam scanning LiDARs that we've been discussing? Basically, the single beam LiDARs scan across a plane, which is not good enough for self-driving cars, because you need to be able to see short objects. You need to be able to see signs hanging overhead. So what people figured out early on is you'll just take one of these 2D scanning systems and you'll just nod the unit up and down so that you scan the 3D environment around you. Now this has a big problem in that it takes a long time. It misses a lot of points, so you get very low resolution in the point cloud. And because it takes a long time, the refresh rate is very low. And what the refresh rate is how often does the scenery update? Like this 3D point cloud is what the world looked like several minutes ago versus a few seconds ago. And in a self-driving car, you really want to be able to update the scene several times every second. Now, with those early types of LiDARs, if you mounted them on a moving car and you tried to sweep the three-dimensional environment around the car, this is what you would get, a very, very low-resolution, low-quality point cloud that you can't really make out the objects in. For example, maybe you can tell the road is flat in front of the car and that there's like some kind of objects on the sides of the road, but that's about it. It's a far cry from the nice picture we were looking at just a few moments ago. This slide just summarizes the points I've already discussed, which is scanning generates very low quality point clouds because you're scanning a three-dimensional environment using an inherently one-dimensional single beam LiDAR. And you need to sweep that in at least two directions. And then it takes too much time, leading to low resolution and a low refresh rate. And in addition, there's a very fundamental limitation that you have to understand when you have a single beam is that you have to wait for the laser to hit the target, come back, and then you can sweep. So it's a very mechanical process, and it takes a long time. It's just inherently limited by the fact that you only have one laser and one detector, and you cannot take more than one measurement in parallel. So when the Department of Defense looked at this in the early 2000s, they wanted to make self-driving cars for military applications and combat zones. And they realized that the ongoing research and development programs were actually, they were not good enough. They didn't see anything promising. And so what they did is they instituted what's called the Grand Challenges, which were a contest for anyone who wanted to enter, usually academic institutions or big companies. And the point of these was to try and build a self-driving car in a simplified environment. They used, in the first two Grand Challenges, they used a desert course. And in that course, you have two main requirements for sensing in the environment. One is sensing, which is mapping out what it looks like. Is there other cars? Are there other cars near you? Is there any obstacle in the way? And you also want to be able to map out the terrain underneath the car so that you can localize the car on a map and figure out where it is and where you want to go if the car is going to drive itself. So in 2004, the first course took place in the Nevada desert, and no team was able to complete the course despite the relatively simple nature of the challenge being in a desert and not too many obstacles around. Now, so the DARPA doubled the reward, and in 2005, the challenge had a $2 million prize, and 5 teams completed the course. The Stanford team won, and the Stanford team was led by Sebastian Thrun, who later went on to found and lead the self-driving car project at Google. Then in 2007, the challenge got a little bit more complicated. They wanted to see if you could figure out a way to run self-driving cars in a simplified urban environment. So they used a closed Air Force base. And in this contest, several teams completed it, and CMU, Carnegie Mellon University, won the race. And that team was led by Chris Urmson, who also later, after Sebastian Thrun, led the self-driving car project at Google. Now, what did the DARPA contestants learn from these grand challenges? What they figured out is that you needed to use different sensors in combination to be able to get you a view of the world. And so many of the teams would use LiDARs, radars, and cameras together. Now, LiDARs we've been discussing, so we should be familiar with by now. But radars have an inherent disadvantage in that because they use radio waves, the wavelengths are very long, and the resolution is just limited. You can't get a sharper resolution as you can with LiDAR. And cameras, the inherent problem with cameras is that you rely on outside light to take pictures. So if it's night out, if it's dark, if you're under shadows, if the sun's too bright and it's blinding your camera, you can't really see. Now, this is still a developing area, so no one knows what combination of sensors, commercial self-driving cars will have. But not everyone thinks commercial self-driving cars will have LiDAR. For example, Tesla opts not to use LiDARs in their systems. there's a regulatory framework in the context. So DARPA really started a lot of research and development in this area. Eventually, the NHTSA instituted a regulatory framework that really maps out the self-driving car classification from level 1, which is assisted, very simple self-driving tasks. Basically just like follow the car in front of you, adaptive cruise control. And for that, you can use very simple like 1D LiDARs. You don't even need to sweep them perhaps. And then levels 4 and 5 are the most complex. When you talk about self-driving cars, you really are talking about levels 4 and 5, which is no human driver is needed, basically. What did the DARPA teams use in terms of LiDARs? Some of the early commercial systems that the DARPA teams used were Regal and Seek LiDARs. These are 2D scanning LiDARs of the types we've been discussing. But there were also options with the multi-beam scanning LiDAR. So this is an extension of the principle of the single beam scanning LiDARs, but now you have multiple beams, one on top of another, so as to get a better view of the world. For example, in this patent from 1993, you could be able to make out the stop sign by shooting 4 light beams, laser beams added. The main disadvantage, as Mr. Jaffe briefly mentioned, is that doing so really complicates the optics. But it was known that, people had done it in self-driving ranging cars. At the time of the DARPA challenges in the late 2000s, there were commercial systems such as Ibeo's Lux system that could use 4 scanning beams to sweep the environment so as to get a little better 3D sense of what's around the car. One of the teams in the 2005 challenge actually developed their own LiDAR system, which was a 64-beam LiDAR system that had a 360-degree field of view horizontally and a 20-degree vertical field of view. This was Team DAD, which was composed of 2 brothers, David Hall and Bruce Hall. They ended up commercializing this system under the company Velodyne, and this is depicted here. Their system was called the HDL64. This is a good example of how complicated the optics can get when you have a lot of beams. I'll show you an image that's still oversimplified. Basically, the Velodyne system has 2 optical cavities, one on top of each other, and each optical cavity has 3 sets of lenses, 2 transmit lenses on the outside and 2 receive lenses, which are slightly larger in the middle. Now, you shoot outgoing beams from the transmit lenses, and then you receive the incoming reflection in the receive lens. And you do that a lot of times. Here we've only depicted it 4 times, but in reality there's 64, there's 16 behind each transmit lens. And this goes on very fast as the whole unit rotates. In 2007, however, at the Urban Challenge, people realized that the Velodyne sensors were pretty good, but they were not good enough for urban driving. And the main problems that people found out was that it had insufficient angular resolution at long ranges, and it was a very unwieldy unit. And how unwieldy is illustrated in the next slide, where we show an 8x8x11 unit that weighs 28 pounds. And this is meant to be mounted on top of the car, so it's going to be a really big, ugly contraption on top of the car. Not only that, because it's so unwieldy, partly because it's so unwieldy, its price is over $70,000, which is more than the cost of most cars out in the world. And this last slide is meant to illustrate a little bit of why the system is so expensive and why the optics are so complicated. And the main point is that manufacturing lenses is challenging, and you can never really get 2 lenses the way you've designed them. There's always some kind of manufacturing tolerance that introduces error into the system. And so what you need is to align each laser diode perfectly with the receiver on the other end. But because of the lens imperfections, you don't know exactly how the alignment is going to work out until you actually build the system and test it out. So Velodyne thought of doing a laser diode, placing 1 laser diode on each board as shown in the middle figure here. And that would allow you to manually align each laser so that, if you see that when you're getting a received signal back, you're actually missing the detector slightly, you can slightly move the laser diode so that the beam adjusts orientation. And this is a very painstaking and expensive process because, remember, there's 64 of these, and you have to repeat the process 64 times, leading to a very expensive overall system. Now, I'd like to turn it back to Mr. Jaffe to conclude our presentation. Thank you.